All right. Hello, everybody. It is our pleasure this week to have Professor Liz Munch giving our 1W-MINDS seminar talk. She is a professor here at Michigan State University in both computational mathematics, science, and engineering and mathematics departments. She received her PhD from Duke University back in 2013. I believe we overlapped, so I was a postdoc there during the same period of time. She then went on to be an assistant professor at the University at Albany, and then moved over here, thankfully for us, to Michigan State University thereafter. She has a wide array of experience and publications in topological data analysis and related techniques, is a recipient of an NSF Career Award, and is generally an excellent speaker. So I'm looking forward to turning things over to you, Liz, and I'll let you take it away from here.
Oh man, I got to live up to that, Mark. That's concerning. Well, thank you all for the invitation, and it's always nice to have this going on. Thank you for, I'm sure my class, now granted I conned them all into coming, but thank you to from my class for giving me an excuse to cancel class today. So we're doing this instead of going to class, which is great. What I'm going to talk about today is kind of a wide array of stuff that we've been doing under the auspices of using persistent homology combined with networks and some other sorts of representation of time series to do things like classify behavior. What we're going to do, well, let's at least start with a sort of required TDA slide, which is that if you work in topological data analysis, you have to run around saying that data is shape, and there is things that we can measure about shape in data. And so there's a lot of different ways of measuring or talking about what we mean by shape in terms of what sort of shapes we can measure or what we think that we're looking for. In a lot of applications and places that we might be using these sorts of tools, shape is sort of in the obvious sense where I'm actually looking for a shape in 3D and I'm trying to measure something about it. Today's talk is a little bit weirder because we're going to study shape and structure of something that is less obviously about shape and structure. And so the work today is going to be mostly about taking time series, trying to represent them as some sort of structure, hopefully because you got it from some sort of underlying dynamical system, and then using that representation as something that we can go try to measure with all of the tools from TDA. So yeah, a lot of what we're going to do, I'm going to make some assumptions about, I'm going to assume that the input data I have is some sort of realization of a dynamical system. And either you handed it to me as a time series and I have to go reconstruct this, or maybe I have the actual underlying dynamical system and I can say things about what the actual attractor is. But what we're going to do is we're going to try to find ways to, in a data-driven manner, come up with quantifiable representations of the shape and structure of the attractor, and then hopefully try to connect that back to the properties of the original attractor, right? So this is the example of everybody's favorite Lorenz butterfly example from a bunch of different choices of parameters. If you mess around with some of the input parameters to the Lorenz system, you can get all sorts of different behavior. So in this case, periodic for some choices and chaotic for others. And so they clearly have different looking structures, and we can try to measure them with various standard tools. And what we're going to do is try to see if some of the tools from topological data analysis can also see a lot of these structures. All right. So to that end, just about every TDA pipeline looks something like this. Today is no exception. So you have some sort of input data. And again, either it's something where I'm interested in shape and structure in the obvious sense, or maybe like today, it's going to be things like time series analysis, time series sorts of input structures. The goal is usually to find some sort of topological signature that you can use to encode something about the underlying shape and structure. And then hopefully, if that is useful, take all of these topological signature representations and be able to do some sort of analysis on them, right? So machine learning, statistics, have access to distances, all sorts of quantifiable ways of, if I have, well, I guess in this particular picture, 300 little grape leaf plants, and then I have 300 representations of whatever topological signature I have, I need to be able to compare those things and talk about sort of similarities and differences and how I can quantify that. So to that end, a lot of the stuff that we do in TDA is aiming for the following goals, right? So I want to have summaries of the shape of data that are hopefully nice in some pile of collection of ways I mean nice. The first one should be that if I have input data, I should be able to use a computer to actually output whatever that thing is. So this should be something quantifiable where I actually hand you a thing. Concise in the sense that it should be smaller than whatever your input data was. So it should be some summary of your input information. Comparable refers to the fact that I really want to have access to things like metrics, so I can talk about how similar two of these representations are, hopefully as a proxy for how similar your original input shapes were. And then robust in the sense that if you have an ability to compare some of these output summaries, but if I happen to have a noisy version of my input data, that should give me a very similar topological summary to whatever the ground truth would have been if I didn't have to deal with that noise. So if you hang around TDA people, the topological signatures that tend to float around, as I view them, can be kind of clumped up into two piles. So there are the more algebraic flavored versions. And so these are the ones that tend to come from anything where you're looking for things like persistent homology, anything related to homology, Euler characteristics, Betty numbers, anything in that direction. That's most of what we're going to talk about today, is use these algebraic tools. There's another family of topological signatures that show up all over the place and I think are very interesting in and of themselves. So Reeb graphs, mapper graphs, merge trees. And in that case, rather than having a sort of algebraic representation, you tend to have some sort of graph that represents your data. The stuff I'm going to talk about today, while we are going to use graphs and networks and sorts of representations like that, are not actually the graphical signatures. We're going to do persistence on the graphs that we're getting. Okay. So, all right, the plan, at least to start. So I'm going to talk about a sort of pipeline we can use to start thinking about taking a time series and turning it into something with TDA tools that I can use for some sort of characterization and representation. So the first thing we're going to do is kind of follow the standard pipeline, as standard as any of this stuff is, but taking a time series, coming up with some sort of approximation or some approximate representation of the attractor, coming up with some way of building a simplicial complex off of it, getting a persistence diagram from that, and then trying to turn that into some vector that I can actually use in machine learning or whatever I want. And then what we're going to do is we're going to start swapping that out with the idea that I can come up with some network representation. So instead of this, I can build some other sorts of representations of data that actually give me a graph that says something about my underlying attractor, and then try to encode the shape of that graph in some way that we can use TDA methods. Okay. So let's start by trying to define any of the stuff I'm talking about. Okay, so our first trick is that if you hand me time series, I want to study the shape of the attractor. And one common tool for doing this is what's called, depends on who you ask, Tokens embedding, delay coordinate embeddings. Those are two main ones I hear this called. But here's the general idea. You hand me a time series. I intelligently pick a dimension, which, do I have that labeled here? M, and a delay, tau. And so based on that information, what I can do is I can look at M different points from my time series, each spaced tau apart from the last guy. So if I have, let's see if I've got this here. So if this is xi, this thing is xi plus tau, this thing is xi plus 2 tau, are those 3 dots on the bottom. And then I have the function values associated to them. So the blue dots are the ones that are directly, or sorry, that should have been ti, sorry, my notation. I should follow my own notation. Ti plus tau, ti plus 2 tau. And then the function values that are associated to those from the time series, which are xi plus tau, and xi plus 2 tau. And the idea is that if I just take those 3 numbers, okay, M is currently 3. If I take those 3 numbers and I think of those 3 numbers as coordinates in R3, then I get a point in space. So the 3 dots that I've marked here happen to be the ones that are at this red triangle location here. And the game is that if I start moving TI off to the right, and I start looking at sort of this cone that slides along, each of these locations gets another data point in space and gives me a new point in this point cloud that I can build. And the game is that if you've hopefully done a good job of picking all of your parameters, you end up with some nice reconstruction of the attractor, at least a decent reconstruction of the attractor. So in this particular example, I have periodic-ish looking data in my input. Periodicity this way turns into periodicity in terms of my circular structure. Unfortunately, I can't make this thing do videos, but if you can imagine that red dot spinning around the loop as you sort of slide this picture along. So that's sort of our first step. So once I have some input time series, I'm going to turn it into this point cloud representation and then try to start analyzing that point cloud for some sort of shape and structure. All right. So here's back to our example that we were using with this Lorentz system from before, right? So my Lorentz system is built on these 3 differential equations. And of course, the Lorentz butterfly that everybody shows when they're looking at pictures are a very specific choice of sigma, beta, and rho, at least in this particular notation. But what you can do is you can start messing around with those parameters that control your dynamical system and get different sorts of output behavior. So in this particular example, different choices of rho correspond to relatively different output sorts of structure. And one of the ways that we can start measuring that is by looking at the Lyapunov exponent. Now, did I put that on the next slide? I did not. We'll talk more about the Lyapunov exponent later when I have actual pictures for you. But the game is going to be, I'm going to start messing around with my control parameter. Any choice of my control parameter spits out a point cloud approximation of my attractor. Now, can I do something with my point cloud my point clouds and my attractors to analyze them to see if I can put them into buckets? This particular choice of rho actually gave me chaotic behavior or periodic behavior or something to that effect. All right, so to do that, I need to be able to take these point cloud representations up on top, and I need to be able to find some representation of their structure. So the tool we're going to use is persistent homology. So let's start with what is homology before what is persistent homology. So homology, the idea is, this is an algebraic object. I am an applied topologist, which means everything in sight is a field, which makes my all of these representations vector spaces. And it's a vector space for every positive dimension, which measures something about structure of that dimensional size. So 0-dimensional homology measures something about connected components. 1-dimensional homology measures something about loops. 2-dimensional, you can think of it in terms of voids, like any sort of 2D space that encloses some sort of air bubble. You can write down the higher dimensional stuff. I have a harder time telling you what exactly it means, but we can still write it down. And so the game is, I can look at this homology as some representation of what's going on with my underlying space. So in these examples, I have a single point, I have a loop, I have a torus, I have a Klein bottle. They all have a single connected component, so their homology is all a rank 1 vector space. But in terms of loops, the single point space has no loops. So it is, sorry, dots here really mean the 0 vector space. My circle over here has a single loop, so he has a dimension 1 vector space. My torus, if you can convince yourself of that, has 2. There's the one through the middle of the donut and one around the top, etc. So this is helpful, but not useful enough for what we're doing, because it is a single output vector space of whatever my my input shape is. What I really want to do is I want to deal with this stuff with point clouds. And if you hand a point cloud to this particular structure, all it does is it gives you a bunch of disconnected components because you got a bunch of points and there's no information to be had. So what we're going to do is we're going to look at persistent homology instead. So the game with persistent homology is that I'm going to start with some information that looks something like this, which I'm going to do definition by example. So the idea is that I have a filtration of a simplicial complex. The only definition for a filtration of a simplicial complex is just a nested inclusion of simplicial complexes one into the next. Technically, everything I'm saying, you can have more complicated maps between things than inclusions, but for the purposes of what we're doing, just add a few more simplices at a time going up in dimension. And sorry, if simplicial complex isn't a word you're used to, all I mean by that is graphs have vertices and edges. Simplicial complexes have higher dimensional structures like triangles and tetrahedra and things of that nature. And so the game is, I can study this filtration of a simplicial complex by studying the changing homology of each of these spaces, right? So in this particular case, I have two connected components to start. And so H0 is going to be my vector space squared. Let's see, I've got no loops, no voids. And so you have a bunch of zeros over here. And then going to the next guy, I still have two connected components. Nothing's really changed in terms of loops. Nothing's changed over here. This guy has, well, now we've gone down to one connected component. Sorry, that's supposed to be Z2 squared. That's just Z2. This thing is, oh, I got a loop. That's nice. And then this thing is still 0. And this thing should still be 0. My loop got filled in, so this guy is 0. And this thing is still one connected component. So the idea is that once you study these sorts of things, you can sort of watch how these numbers of connected components or loops sort of maintain themselves. There's a lot of additional structure under the hood that I'm not really talking about, which is that not only can I just keep track of counts of how many generators there are at every space, I can keep track of who actually matches to whom. And so there's actually a bunch more information here in terms of when does a connected component appear and then start merging with a neighbor, or when does a loop appear and get filled in. But for the purposes of what we're doing, let's pretend that's magic and I can just output that as some sort of representation. So actually everything, the magic here is actually a whole bunch of just matrix manipulations that are long and nasty. Yeah, we'll just keep that under the hood. All right, so the idea here is that if you want to keep track of when structures appear and disappear, there's a time when they enter, there's a time when they go away. And so what we do is we represent this in terms of a persistence diagram. So for instance, the connected components that I had two connected components to start, two connected components sticking around over here, and then they merge into one. So one of those we're going to decree to have died. Sorry, we're very morbid. And so I have a connected component that was born at 1 and dies at 2. Is that what I want? I feel like there's an error with my 2 into 3. I think my numbers might be off. That's cool. I should double check this example later. In any case, the idea here should be that I have a connected component here that sticks around, but then merges into the other connected component. I have another connected component that sort of lives forever because there's one connected component for forever. And then I have a one-dimensional structure that shows up here and gets filled in over here. So what we can do is we can represent this information in terms of a persistence diagram. So I keep a point in my persistence diagram for basically in my intervals up here. Hopefully I've actually done them right for this picture, for where they start and end. So I think this guy is 1 into 2. Never check your example in public on a recording. Okay, so this persistence diagram should be, I think, 1 lives forever, 1 dies entering 3, and then 1 is born at 3 and dies entering 4. These two are 0-dimensional pieces of information. This guy is a 1-dimensional piece of information because it's got to do with whether it was a loop structure that showed up or connected components structures that showed up and disappeared. The point being, what I can do is I can take this information about a filtration. I can turn it into this persistence diagram, which is now just a bunch of pairs of points in the plane that have to do with when a structure appears and disappears. And we can use that thing as some representation of my data. So where do I get that from my point cloud information? So my input data, what I'm going to assume is that I am handed a point cloud living in RD. What I really care about with the point cloud is I care about knowing pairwise distances. And so the way that I can get a simplicial complex, and more specifically, the way that I can get a filtration of simplicial complexes, is building a construction that's called the Vietoris-Rips complex. So the idea is that if you hand me a point cloud and you fix a particular distance parameter, what I can do is I can think about having basically a union of disks over top. Oh, no, nope, this is the wrong explanation for this one. Sorry, let me back up. What I can do is I can think about all pairwise distances between these points. And if 2 points are within distance epsilon of each other, then what I can do is I can add an edge to my simplicial complex. Then what I can do is I can add higher dimensional simplices wherever possible. So in this particular example, I have a point cloud with 4 different points. I can look at the essentially overlaps of these balls. These are supposed to be the ones that are at distance, well, in this case, 1/2 epsilon. So as long as you're in distance less than a half or less than epsilon, we're going to add an edge between the 2 of them. So that's what I'm getting with these edges and things over here on the left. And the trick is that if I have the ability to put in a higher dimensional simplex, I do. So in this particular case, because I have all 3 of those pairwise, I've got all 3 pairwise edges, so therefore I get the triangle included in the middle. The fun trick here is also that this creates a filtration of a simplicial complex, because as long as epsilon is less than or equal to epsilon prime, the Rips complex of x using epsilon is included in the Rips complex of x using epsilon prime. Okay, so I can build this Rips complex, and then we can start looking at this on more complicated examples. So in this particular example, what I've done with a very much synthetic example is mess around with the idea of taking the same point cloud. So each of these pictures has the same collection of dots, and then start trying to match up points based on some proximity epsilon. So in this case, my radius is an increasing parameter, and I'm going to keep track of, well, I can keep track of when connecting components show up and start merging together. This is a little more interesting if I think about the loop structure. So overall, you can start seeing the loop structure by looking for when, well, a circular thing with a hole in it shows up and then when it fills in. So for example, I've got some sort of, oh, that color is not going to show up, is it? I've got some sort of circular structure that shows up over here. It's still hanging around, and then it fills in over here. And so we should have some sort of relatively early point in my persistence diagram representing something about a circular structure that shows up and then fills in pretty soon afterwards. Then I also have this global structure. So I have the big outside loop, which I think the first time, at least in these pictures, it shows up is somewhere around here. And again, I can kind of keep track of when this thing shows up and fills in. This is a nonlinear thing. So this started around radius is 0.9, and this thing is, so these pictures are doubled, so that's around 2. So somewhere around 2-ish, and then fills in over here. So the game is, again, if I have some sort of circular structure, especially in my data set, what I can do is I end up with a persistence diagram. And then the perk of this is that it's also, at least in this setting, encoding something about geometry. So it's encoding something about the size of the hole that is showing up. So in this case, because I had a little hole that gets filled in at a relatively similar radius value, that shows up as a point kind of close to the diagonal. If you appeared and disappeared almost immediately, you'd be on the diagonal. And so then if I have a bigger hole structure, that's going to show up as a point further from the diagonal. So these are the sorts of input representations we're going to use as our proxy for representing something about this realized dynamical system. Now, persistence diagrams are kind of awful to work with, and I can say that having worked with them for a long time. So what we tend to do with a lot of these things is find a way to represent them as some sort of other vector, hopefully in a nice enough way that you can pass this into machine learning. So to that end, there's a whole host of ways to do this, some of which are shown on here. So you might have seen versions of this before. So there's persistence landscapes, which involve coming up with a whole bunch of functions that represent something about your data. There's persistence images that turn your persistence diagram into some sort of, well, discretized image, which you can then use to pass into whatever your favorite machine learning tool is. There's template functions, which is another way of coming up with some sort of vector based on some little tent functions that you sort of use to probe your space. For the purposes of today, all you have to know is that I take some of these persistence diagrams and turn them into a vector, and then we're going to start doing things like machine learning on those guys. Okay, so that's the standard version of how we tend to do these analyses. So I tend to start with a time series, turn this into some sort of tokens embedding, do a RIPS complex filtration, then compute a persistence diagram, and then do some sort of featurization to get a vector out at the end. So here's at least one example where we're playing around with this. So this example is computed on, I think, the Rossler system. Yeah, the Rossler system. So I have a bunch of realization of time series from the Rossler system, and then I can do things like go back and try to reconstruct the attractor. And so again, what we were doing was trying to figure out how similar these things are, or how much can I use the time series or how much can I use the topological representations as a proxy for something about underlying structure of the attractor or behavior of the attractor. So as a proxy for ground truth, what we did was compute the maximal Lyapunov exponent of the time series for a varying parameter. So this is an alpha parameter. Oh, no, come back. So for different choices of alpha, which is a parameter in my dynamical system, every choice of alpha gets me a new realization of my dynamical system, or of my output time series. And then we go through this whole process, right? And so I can either decide whether or not this thing is periodic or chaotic by looking at the maximal Lyapunov exponent, which basically the question then turns into 0 versus 1. Or what I can do is I can measure this in terms of my persistence diagram output and train a classifier on this thing that basically takes those things as input and then spits out whether or not it thinks that something is periodic and chaotic. So this was kind of a nice proof of concept, which was, again, we're doing this for a whole bunch of different realizations of time series. The ones that are misclassified are marked here. And in this case, this is a little difficult to interpret. Every time you misclassified it once, we showed it as every location on the local extrema. So that line of dots is actually like one misclassification. So what ended up happening, we misclassified things exactly where we expected to misclassify things, which is on the border of whether or not this thing was periodic or chaotic. So in general, if you are very clearly periodic, then it's doing a good job. And if you're sort of on a boundary case, well, that's kind of a reasonable place to be making mistakes. So this was sort of a first pass example of sort of trying this out. But the big problem with this is that, well, yes, the persistent homology can do wonderful things in terms of encoding the shape of the attractor. The downside is that point cloud persistence is not something you want to do all the time. It is not the best computationally. The software has gotten miles better than it used to be, but it's still rather limited in terms of the size of the point clouds you can actually work with. So to that end, what we wanted to do was see if we could find some sort of smaller representation of your underlying attractor that still encodes something about the shape and structure, that's still relatively easy to compute from your input data, but hopefully is computationally less icky. Okay, so what we're going to do is we're going to talk about taking your time series and coming up with these network representations instead. All right, so
could I ask a quick question first?
Yeah.
Very general question. What's the sort of the computational bottleneck right now? Is it high dimensional data? Is it the number of points that you have in your data cloud, or all, or neither?
Mostly the number of data points in the point cloud. I'm going to assume that you handed me a distance matrix. So that problem has its own issues, but let's say you just handed me the giant distance matrix. The issue is that a lot of the numerical tricks you can pull on matrix manipulation problems don't work here because there's a lot of 0-1 matrices, and yeah, the numerical tricks just usually don't apply. And so we're stuck with a whole bunch of algorithmic awfulness. So there's some papers that say that persistent homology is something like O of n to the omega, where omega is, matrix multiplication time, I think.
Mm-hmm.
And then the big secret that everybody's hiding is the fact that n has to do with the number of simplices, not just the number of data points you started with. And so if you want to, exactly, right? So you can limit it, you can make it better, right? So if I max out the dimension I'm working with, that limits the number of simplices. If you aren't interested in the entire RIPS complex from 0 to infinity, you can kind of limit the size of your spaces. And there's a bunch of ways of like kind of getting around this, but some of them have more theoretical justification than others. How about that? But,
All right,
so,
cool. Thanks.
Yep. Okay, so we're going to make things smaller. All right, so network representations of time series. So what we're going to do is we're going to work with this construction that's called the ordinal partition network. All right, so here's my input time series, which for the moment is very nice, but could have been uglier than this. I'm going to pull a similar trick that I did with the tokens embedding, where I choose a dimension and I choose a tau. And what I'm going to do is, rather than entirely remembering all of the locations of the points, what I'm going to do is I'm going to keep track of essentially the shape of the little picture I would have drawn based on connecting those points one to the next. Equivalently, if you are an algebraically minded person, you can think about this as partitions or permutations of sets of endpoints. So in this case, I'm keeping track of n different, or I'm going into dimension 3. I'm looking at all different permutations of 3 different numbers and just keeping track of, at any particular location, which of these permutations am I working with. We have these sorted into an order labeled pi 1 through pi 6, but these are not in any important order other than the fact that I'm just going to keep track of which one it is. All right, so you can play the same game. If I take this sort of set of 3 numbers and start sliding it along and seeing where these points hit, what happens is you move around and you switch from being pi 5 to one of the other permutations and so on and so forth. And so what we're going to do is we're going to keep track of that in a graph. All right, so here's my example graph. So I've got, again, my permutations are sort of tracked with numbers on the left, but order doesn't really matter. What I really care about is the fact that as I slide along my starting locations, what I'm going to do is I'm going to jump from one partition to the next. So in this case, I'm going to jump from, sorry, I keep saying partition, permutation to the next. So in this case, I'm going from permutation 1 to 2 to 5 to 6 to, what is that, 4, etc. And what that means is that I am going around 1 to 2 to 5 to 6 to 4 and running around in this graph where I can just keep track of this information. So the full information that I have to start is actually a weighted directed graph, right? So I know how many times I passed from one vertex to the next. And I also know that I started at one vertex and went to the other one versus the reverse. For some of the stuff I'm going to say, we're going to forget some of that information, but the full ordinal partition network sort of keeps track of all of that. So the fun thing to notice here in particular, so this is sort of a non-noisy version of my original example with periodic, a periodic looking time series. If you can unfold this graph in your mind, this thing is actually just a loop graph. So it's a cycle graph where I'm just going around in a circle. And that is helpful because if I'm looking for the shape and structure of this thing, before we had periodic behavior being circular structure, this is still periodic behavior being circular structure. And so it's hopefully a good representation. Okay, so now what I've done is I've started with time series and I've built a bunch of graphs. So now what I want to do is figure out a way to take these graphs and pass them to persistent homology constructions to be able to actually come up with some sort of representation. So here's version 0 of that. All right, so you get me a graph. What I can do is I can keep track of distances between vertices in that graph. So for right now, I'm going to forget the fact that I have a directed graph. I'm going to forget the fact that I have a weighted graph. I'm just going to look for shortest paths between my 2 vertices. And so what that does is that gets me a distance from one vertex to any other vertex. And it turns out that everything I said before with my RIPS complex information doesn't care that my points were in Euclidean space. It just cares that I have some sort of pairwise distance. So because I now have a pairwise distance, I can think of building this RIPS complex. Now, what's a little bit weird to think about is that my RIPS complex is now technically a filtration that is on the complete simplicial complex, where I have every possible vertex or every possible edge and triangle everywhere. But there's a few things that are related. So for instance, oh, I lost my labels. Okay. So if I have my RIPS complex at distance 0, that is all the vertices that are at distance 0 from any other vertex, and that is just the vertex set. Everybody who's at distance 1, if I add in all the edges that are at distance 1, that's now basically putting back my graph. That's my graph. But then what happens is as I increase, so this is distance 2, distance 3, distance 4, distance 5, what ends up happening is I start putting in more and more edges and adding in more and more corresponding triangles. And what basically gets measured is the fact that I clearly have two sort of loop structures in this particular graph, and I can keep track of when they showed up and when they filled in. One particular thing to note in this case is that my loops in this case are always born at distance 1 because they always show up when the graph has all of its edges. And then you're interested really in when they actually fill in. So something about the size of the loop. So in this case, sorry, they're a little bit small. I have two different points. No, come here. I have two different points in my persistence diagram up here saying something about the fact that I have two loop structures that are showing up. All right. So let's put all this party together. So if I have input time series, I build these ordinal partition networks. And proof of concept number 1 is the fact that if I have a periodic looking signal versus a chaotic looking signal, the resulting networks are very different in terms of their underlying structure. So one has a very obvious loop structure, the other one is kind of a hairball. And the persistence diagrams are very, very different. So please note that these are different heights. So that's somewhere around 7, that stops somewhere in there. What I have is I have two very large persistence points in my diagram in the one case, and in the other case, I have just a whole bunch of stuff that's relatively close to the diagonal compared to the other guy. You can have duplicated points and overlapping points. So for some of these pictures, I'm going to show histograms on the side, which are basically just showing how many points are actually sitting drawn on top of each other that I can't actually show. So in this case, you've got a whole bunch of noise. This thing is, I don't know, 15-ish points in my persistence diagram. Okay, so this gives me a way to go from a time series to a network to a distance matrix to a persistence diagram, and then I can choose my favorite way to represent this in Rn. So let's take a look at what was going on in here. So in this case, we were doing things with the unweighted graph. Oh, I don't actually have the definitions of these things, but the general idea here is that I can take my network and try to take that persistence diagram and find some way of encoding information about the persistence diagram. In this case, we were going for simple. This was just a number that says something about your persistence diagram. So in this case, we did things related to information. We did number of points. We did, I forget what M was exactly. So for different choices of output measurements, we had different values coming from the persistence diagrams. Everybody down here is a TVA related measurement. And then I've got my Lyapunov exponent. And so the first proof of concept was just that, at least if you squint at these things, the sort of representation numbers that you get tend to follow the shape of the Lyapunov exponent. Not perfectly, and you have to kind of, there's not exactly a nice cutoff, which is a little bit frustrating, but they're at least representing something about the underlying shape and structure. What is nice is that when you have a decent amount of noise, you can still kind of differentiate what's going on. So in this case, this was my chaotic values versus my periodic values versus signal to noise ratio. So if you have more noise, I'm going to have a much harder time of figuring out what, or figuring out how to compare my different time series or my outputs. But as long as you have a relatively decent signal to noise ratio, we can start differentiating these two classes based on these various numbers we were computing. But this is still a little unsatisfying, in part because I have forgotten a lot of information. So I was handed a bunch of networks that were directed and had a bunch of weighting information. And if I forget the weighting information, you can get all sorts of weird stuff happening. So here was an example we came up with where I have two different graphs that are very, very similar with the one exception that they have a heavy weighting around this loop. And if I add a little chord across the middle of the graph, this can massively mess with the results in the previous thing. So in this case, what we did was we messed with a bunch of different ways of coming up with distances between pairs of points that started incorporating information about the overall structure. The shortest unweighted path, so this is the version where I just forget all the information about weighting or anything else, and I just do what I was doing on the last slide. And in this case, these two graphs look very different from the persistence diagram standpoint, because one of them has a point that's far from the diagonal, and the other one has two that are less far from the diagonal. Sorry, again, that's a 6 and that's an 8, so this one's considerably lower. And so if I want to say that these two structures are basically the same thing, maybe up to that little noisy jump that happens somewhere, we need to incorporate information about the weighting. And so what we did was we started messing with different ways of coming up with a distance between vertices that incorporated weight information from the edges. So here's what ended up happening when you did that instead. So, okay, so sorry, let me explain the pipeline that gets you these pictures. So the idea is that I started with time series. I use a choice of distance measure that has to do with keeping track of all the weighting information. And then I have these output persistence diagrams. And what we did to try to understand these output persistence diagrams was looked at MDS plots of distances between the diagrams. So these sorts of diagrams, the interpretation is points in these pictures represent two different persistence diagrams, and they should be drawn close together if the diagrams themselves are similar. And so what ended up happening with these, so again, in terms of keeping track of different choices of distances, the chaotic things generally hang out together. So the red bits are chaotic bits. The blue bits are periodic time series input representations. And so the interpretation here, at least, is that the resulting persistence diagrams are doing some sort of separation in terms of what's happening with the shape and structure, that they should be sort of separated somewhat. This is not a true machine learning trick, because you can't actually do any sort of train test splits or anything. This is more of just a proof of concept that the persistence diagrams are actually giving me some sort of differentiation in terms of representation. And we'll see if we can talk about some of this. Okay, so let me sort of take a little bit of a left turn and figure out if we can use these and keep track of bifurcations using these tools. Okay, so back to this picture again. Oh, this was the one I thought I had earlier. We'll move it later. Right, so everything I said before, forgot about the fact that I have a continuous row parameter that I was changing and getting a whole bunch of different time series and getting a whole bunch of different realizations of dynamical systems. But really, you can organize these things into a one parameter family of point clouds that should have something to do with each other. So what I would like to do is be able to tell you where in that parameter family something changes, right? So in this particular case, right, if you're using maximum Lyapunov exponent, I'm looking for when I go from things that are non-zero to things that are zero, right? And so can I use the tools that we've been developing to try to decide when that switch happens? All right, so what we did first for this was try to use the fact that you have point clouds that are matched up one to the next and use a tool, it's called zigzag persistence. So what I mentioned earlier was the fact that when we were doing persistence diagrams, I had a filtration of simplicial complexes, which meant one was included into the next, going in a one-way path. It turns out that the algebra is still fine with it if your inclusions one to the next sometimes go the opposite way. So in this particular example, this is a synthetic example that my former PhD student had come up with. What I have is I have a series of point clouds. So, oops. X0, X1, no, not you, X2, X3, etc. And I can create a zigzag of point clouds by looking at the union. So I can look at X0 union X1, I can look at X1 union X2, etc. And I have inclusions going hopefully the correct way that the arrows are drawn. And what I can do is I can try to see when in this particular sequence of things, my structure actually has a loop that shows up and then has a loop that fills in, right? So the first thing to notice is that, again, that top row, all I've done is given you a bunch of point clouds. That is not very interesting. So what we did was we swapped this thing out with RIPS complexes. So at every step, I can pick a RIPS complex. I can fix some sort of RIPS parameter for that. and get now a bigger simplicial complex. So what I've done is picked a bunch of numbers, mostly here via trial and error, so that one is 1, 5, 2, 3, etc. That gets me a Rips complex at every stopping point. And then I can take the Rips complex that you get at the union, and that gives me a zigzag of Rips complexes. And here it's a bit clearer where I could start finding the sort of loop structures where they show up in this procedure and when they fill in. So in this particular case, I've got a loop structure that shows up somewhere around here. He sticks around for a while until somewhere around here. And the fact that that is showing up tells me that I have some sort of one-dimensional structure that's relatively far from the diagonal. Now, the interpretation with these is that now the coordinates on my persistence diagram, rather than being associated to the Rips complex distance proximity stuff, are actually corresponding to the when does this thing show up in this sequence stuff. So now my coordinates in my persistence diagram should be interpreted in terms of bifurcation parameter values as opposed to distance values. And so what we can do is we can start trying to come up with persistence diagrams that measure things about where I think the structures sort of show up and go away. So in this case, so this is I didn't write it down. I think it's a Selkov model, right? So I can do this procedure. So for all of those parameter values, I get one persistence diagram, and then I can interpret points in the persistence diagram as when does some loop structure in particular show up and disappear in the sequence, right? So in this case, the fact that I have a one-dimensional point somewhere around here comes from the fact that I have a loop structure that sort of starts there and continues until there-ish. Right. Now, if you thought computing a bunch of persistence diagrams was bad, this is worse. Zigzag persistence has not had the benefit of a decade's worth of people trying to make the code better. There's some nice things coming down the pipeline soon that I think will make this computationally better, but these things are real bad. But upside is I am handing you a single persistence diagram that now represents something about the entire sequence of persistence diagrams I started with. So, of course, one of the things we started trying to do was, if you swap this thing out with the graph representations, what happens? And so we've been playing with this idea where, again, you have ordinal partition networks now instead of your point cloud persistence. I can work with much smaller graphs because now instead of having the entire point cloud, I have just the number of permutations, which is something that I can control. And in particular, I get a single output persistence diagram where I can read off information about it in terms of the bifurcation parameter as opposed to size of loops. So here, so I've got all of these different highlighted points in my zigzag persistence diagram. These things correspond to regions of parameter of bifurcation space. So in this case, that point right there has something to do with the fact that in this intermittency project that we were working on, there's a region where I have a periodic behavior that then becomes chaotic for a little bit before becoming periodic again. So let's see. We can start playing with some other stuff. So the first thing the next thing that you can do is to try to get rid of persistence entirely. So there's these really nice constructions that are called Crocker plots. So these were originally used in terms of studying time varying point clouds in aphids. But one of the things that you can do is you can swap out your persistence information with just Betty curve information. So Betty curves are, rather than keeping track of all the vector spaces and the maps and the things that go between them, you can keep track of just the rank, the dimension of the vector space at a particular location. This is strictly less information than the full persistence diagram, but still useful. And so what you can do is swap this thing out for this Betty curve function information. And for each value of my particular, let's see if I can get this guy to line up. So for each value of my row parameter, I get a Betty curve. Well, I get a persistence diagram, but I can backfill and figure out a Betty curve. And that Betty curve information turns into a column in a matrix. And so then what I can do is, well, mess around with my row parameter. I get a bunch of these different columns in my matrix and start studying this thing as a heat map to see what's going on. So here's where we've been messing around with this idea. So again, this is that Rossler system again. If I do this Crocker plot construction where now, oops, these two pictures, these two guys right here, these are essentially encoding a bunch of stuff about that persistence diagram information. What's super helpful, even without computing all of these awful persistence diagram giant representations, is that you can see like very distinct switches in structure. So like somewhere around there, we've got some sort of switch in terms of information with sort of dimension of all these vector spaces, et cetera. So one of the things we've been working on is taking that information, finding ways to, again, compare it to the Lyapunov exponent, because that's sort of our available choice for ground truth. It turns out that this is also related to things like norms of Betty curves and stuff like that. But for the sake of time, I'll move on. So let's see. I got that with Lorenz. Similar idea where you have these sort of changes in behavior of your underlying system cause pretty obvious changes in behavior of your Crocker plots. Okay, so what are we going to do with this? So just to give you a sense of some of the things that we've been messing around with. So we do have bifurcations using Crocker plots, so we do have that down here, although I think there's still some work to be done to understand why that stuff works as opposed to just having data-driven versions of it. We've been messing around with some other sorts of representations, other choices of networks for representing your time series data. The coarse-grained state space is one that's been particularly useful just because it's a bit more data-driven as opposed to being entirely dependent on some choices you make in advance. I would love to find a way to get this directed information back in there, because we did drop all of the sort of time-dependent information entirely from our time series. So we're working on some ways of trying to get that back, but directed persistence is a bit more of a hairy beast to work with. And we've also done some things that are on the face a lot simpler than anything I've talked about, but it turns out that very simple ideas from persistent homology can be very useful for some more general signal processing problems. In particular, finding zero crossings in time series when they're particularly noisy, pulse counting in noisy sorts of binary time series. There's a lot of really interesting things that are mathematically really simple, but turns out go really fast. So those have been nice. So let's see. Let me point out, first thing is that just about everything I said either is or is going to be included in our open source Python package. So our Python package is Teaspoon. TSP is topological signal processing. The documentation, everything is housed at that top link. You should be able to just do pip install Teaspoon and get it running on your machine. That being said, if you find bugs and things, please let us know. And also, we're happy to have people put in pull requests and get involved, because it's becoming a really nice big library of things that you can do with topological based processes. And this is all collaborative with Faraz Kasawane, who's another professor here at Michigan State. And right now the main leader on this project is Danielle Barnes, and she's been doing a lot of stuff getting this to a really nicely installable state where other people can use it. Let's see, right. So yeah, take-home message. So the real take-home message here is just a lot of these tools are very useful for data analysis. A lot of the time, the trick is trying to figure out how to take your data and represent it as some sort of topological signature that is useful based on the question you want to ask about your original data set. So in our particular case, this came down to finding networks that were good representations of our attractors, and then finding distance metrics on those networks that were actually doing a good job of encoding the structure we thought we were seeing in advance. So to that end, I will finish here. So many thanks to all the people that work on this. So by no means did I do all of this. This was largely collaborative with for us and his and my graduate students over the years. And special thanks to the Air Force, who funded a lot of this project. So, and thank you to all for your attention.
Excellent. Thanks a lot for a great talk. Let me open up the floor now for any questions that folks might have.